Let's continue on talking about the integral test and p-series with some explicit examples. In this case, I have natural log of n over n to the 8th. Okay, so this is going to be one that definitely, when we get things like the ratio test and the comparison test, is going to make our lives a lot easier. But we don't have those yet, so we're going to have to do this kind of the hard way. So when I look at this, I say, okay, I could take the nth term test for divergence, take the limit. Okay, well, that's going to be infinity over infinity. We have to apply L'Hopital's rule. You get one over 8 n to the 8th. I did a little simplification there. Hopefully you feel comfortable doing that by now on your own. So this is inconclusive. Man, all these seem to be inconclusive. It's almost like that was done on purpose. But it's a good idea to do it anyway. It's good practice. So what we want to do is let's set up a function. Now, give me a second here. We do kind of have an issue here. This is fun. This is fun. We have to be careful. We have to be careful. I'm going to tell you why. This is a good example, but it doesn't really fit with exactly the theory that we talked about. Now, it's true, but it's a more general case. So I want to talk a little bit about this. The reason why I say this is, okay, all right, well, you say, is this a positive function? Well, no, it's not. If I plug in 1 for x here, natural log of 1 is 0. Uh-oh. That's not very helpful, is it? Well, it turns out it's going to be okay. And the reason it's going to be okay is, okay, so let's consider the cases where x is bigger than 1. Well, as long as x is bigger than 1, natural log is positive, natural log of that is positive, and then anything positive to a power is also positive. So it's positive for values bigger than 1. Why does that matter? Well, it matters because the integral test, you're taking this thing out to infinity. And so the things that happen in the short term don't really matter, because you can have a lot of wonky behavior, but we're playing the long game here, right? So, you know, the swings that may happen, those are just round off errors. Those are chump change in terms of when we look at the totality of infinity. So as long as we can find some value where once I hit this point, everything after that, it's positive, continuous, and decreasing, then it doesn't matter. So there's a couple ways to do this. One thing you can do is you can take the series and you can split off a few terms and say, all right, these terms add up to some number that's finite plus this series, and then I can apply the theorem on that. And that's a very standard way to do that. The second thing is to sort of hand wave and say, look, those first few terms don't matter. So let's just look at the integral to infinity, and then we'll worry about it when we get there, which is typically the approach I take. But this is a little fishy here. So if we take the derivative, so I'm going to rewrite this as that, because I'm going to use a product rule here. So the derivative is 1 over x times x to the negative 8 plus natural log of x times negative 8 x to the negative 9. So this is going to be x to the negative 9 minus 8 natural log x to the negative 9, which then becomes negative 8 natural log x for x to the 9th. And so we already said we're only considering the cases where x is greater than 1. So, I'm sorry, this is 1 minus 8 natural log x. My fault. 1 minus 8 natural log x. So I got to figure out, where is this thing going to be negative? Well, on the bottom, we're considering positive numbers for x. So the bottom doesn't actually contribute. So what I have to say is, okay, 1 minus 8 natural log x. When is that less than 0? Or equivalently, when is 1 less than 8 natural log x? Or equivalently, when is natural log of x less than 1/8? Or equivalently, when is e, so if x is greater than e to the 1/8 power. So e to the 1/8 power, I don't know, that's like, less than 2 or something like that. So what that tells me is, as long as I'm looking at as long as there's some finite value that says, look, after 2, this thing settles out. It's positive, continuous, and decreasing. So what I recommend you do is take this function, plug it in a graphing calculator somewhere, and what you'll see is it'll start at 0, and it'll kind of come up, and there'll be a bump, and then it'll go down. There'll be right at e to the 1/8, there will be a critical point, and after that it'll be positive, continuous, and decreasing. And as long as it happens at some point and stays that way, you can apply the integral test. I don't love this, but it is important that you get there mathematically. This is a little soon. So anyway, let's keep on rolling. Looks like we have something that's positive, continuous, and decreasing, so we can apply the integral test. And here's where it gets fun. So you might say to yourself, okay, well, I'm going to let u be natural log of x. Okay, fine. Let u be natural log of x. And then du is 1 over x dx. Got an issue here, because I can take care of the natural log of x. I can take care of 1 over x dx, but I got x to the 7th. I got 7 more x's on bottom to take care of. So how do I get rid of that? Well, the way you do that is you use the properties of inverses. So what I can say is e to the u is equal to x, right? If I take e to the u, that's the same as e to the natural log of x. Well, e and natural log are inverse functions, so there's cancellation. So that's the way you can write that. So now what I have u over e to the 7u du. Okay. At that point, well, I mean, and I could rewrite these bounds. That was infinity. I don't know why I wrote 8. I could rewrite the bounds 0 to infinity, because when x is 1, u is going to be 0. When x is infinity, u is still going to be infinity. So this is 0 to infinity of u e to the negative 7u du. So we got to apply integration by parts. So what I look at here, maybe I shouldn't use u substitution. Maybe I should use something called like t substitution. Let's say t, 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 t. Okay, fine, great. So when I've got that, now I can apply my integration by parts formula. I can say u is t, du is dt, dv is e to the negative 7t dt, so v is negative 1/7 e to the negative 7t. And then I can apply the integration by parts formula. That gets me negative 1/7 t e to the negative 7t plus integral 1 to infinity, and that's from 0 to infinity, 0 to infinity of 1/7 e to the negative 7t dt. At which point then I can apply this again. I can say, or I can integrate one more time. Negative 1/7 e to the negative 7t minus 1 over 49 e to the negative 7t from 0 to infinity. nasty, right? I mean, we've done a lot of different things here, but this is also why it's important to have your integration techniques in your belt. So when I plug in 0 here, well, let's try the infinity case first. The infinity case, e to the negative infinity, that's like 1 over e to the infinity, just drives down to 0. Okay? Now, in that case, this drives down to 0, but that drives to positive infinity. So what you have to do is you have to go, all right, what's the limit as t goes to infinity of t over 7e to the negative 7t? Or not 7, positive 7t. Because I'm taking this negative and writing it in there. And if you apply L'Hopital's rule, you get lim as t goes to infinity of 1 over 49 e to the 7t, which then goes to 0. So that also goes to 0. And then we have to subtract the case where t is equal to 0. Well, this goes away when t is equal to 0. So you're only left with 1 over 49. I believe that's right. I mean, I'm going to be honest, I don't know that that's the correct answer, but it doesn't matter. The reason why I say it doesn't matter is if I made an error in the integration, who cares? Because what we're trying to do, I know for a fact this is a convergent integral, so I get 1/49th, that's a convergent integral. As far as I could tell, that's convergent. But that's a lot of work to get convergent. Fun, right? This one isn't going to be as bad, I promise. Let's take a look. We have 1 over 16, square root of 2, square root of 3, square root of 4. Okay, so let's see if we can't identify a pattern. See if we can identify a pattern. Well, it looks like I have the square root of the index on the bottom every time. And it looks like I have a 1 in the numerator every time. Does that make sense? Because this would be like 1 over the square root of 1. No problem. Now I have this. So this is 16. Well, 16 is 4 times 4, which is 4 squared. Okay. And 81 is 3 times 3 times 3 times 3. So that's 3 to the 4th. Well, that doesn't really help me. So what if I instead say 2 to the 4th? Okay, that looks a little more promising. Okay, that's 4 to the 4th. Okay, that's a little more promising. So it looks like what I've got, and this was A2, A3, A4. So this matches. So I have 2, 2 to the 4th, 3, 3 to the 4th, 4, 4 to the 4th. So what if I was n to the 4th? What do you think? You think that'll work? Well, when n is 1, that's 1 over 1, okay. When n is 2, 1 over 16, square root of 2, 3, 1 over 81, square root of 3. Okay, I feel pretty good about this. I feel pretty good about this pattern. So then what I can do is I can say, all right, I can rewrite that as n to the 1/2. So a to the n is 1 over n to the 9/2. Okay, 1 over n to the 9/2. Which would not have been readily apparent by just looking at terms. So pattern recognition is tough. Well, that tells me that we're looking at the infinite sum 1 over n to the 9/2. Well, looky there, we have P series. P is 9/2. Well, P is bigger than 1, or that number's bigger than 1. So it converges. Hey, it's really nice to not have to take a nasty old integration by parts to get your answer, huh? And so, that's just a good example of using the theory of the P-series to your advantage.